Today, we're going to continue looking at parameterized curves that we can stick into a vector field. The first two are going to be pretty important. We're trying to describe a line in three-dimensional space. This is important because we know that if we make a linear equation in x, y, and z, we just write an equation with x, y, and z, where x, y, and z are all degree 1 terms or 0, we're going to get a plane. We don't want a plane. A linear equation in 3 variables will produce a plane. We're trying to describe a line. That's why we needed to bring vectors and parameterized curves into play, so we could describe a one-dimensional line in R3. To that end, we're going to do the same stuff that we did when we were describing lines way back in elementary algebra. We either need a point and a slope, or 2 points. I realize that this is not a slope, it's a direction vector. But the slope is just some direction vector in some weird form, where instead of listing a rise, listing a run, comma, rise, since there's only 2 numbers and we're in a 2-dimensional plane, we just make a ratio out of it. And then we get some more, we get to interpret things a little bit more. So when we say we need a point and a slope, what we need is a place to start and a direction to go. And that's all that we have here. A place to start and a direction to go. All right. So let's look at what we're going to do in each of these cases. Number 1. Like I said, when we want to find the equation of a line, just going way back to elementary algebra, we need a point and a slope. And we can't call it a slope now because we're in R3. So we'll say a point and a direction. That's all the slope is anyway. It's just a direction. What we can do is separate our line and describe x, y, and z independently of each other as functions of some parameter. So I'm going to notice that x starts off at 1 and increases by 2. So I want x to start off at 1 and increase by 2. So I'm going to just say x equals 1 when t equals 0, and x equals 2 when t is equal to 1. Remember what we talked about yesterday. We have a lot of control with the parameter. We're going to make the parameter whatever we want it to be, whatever is most convenient for us. Yesterday, when we were talking about circles, it was most convenient, since we wanted to make a circle, to use our parameter from 0 to 2 pi, because that would get us cosine and sine around 1 time. That's what we wanted. In this case, I need to describe the direction x increasing by 2. So I might as well just use a run of 1. I'm just going to use a rise of 2 and a run of 1. So I'm going to say x equals 1 when t is equal to 0, and x equals 2 when t is equal to 1. Choosing t equals 1 for this was our choice. We're choosing values of the parameter that are convenient for us. It could be that we're in a scenario where I don't want to increase by 2 until 10 units of t have passed. So I'd have to make some adjustments. But this is going to be convenient for us. We just need to describe the direction. We know we're making a line, so the 3 components are going to be linear. So I'm just going to say x of t starts at 1 and increases by 2 every 1 unit. And then we're just going to do the same thing for y and z. Similarly, y of t will start off at -5 and increase by 3 every 1 unit. Similarly, z will start off at 7 and decrease by 4 every 1 unit. And we can just do this for all t. If I'm starting off at 1, -5, 7, since we're making a line, it doesn't matter how far we go, the ratio should always be the same. So if we take a step of 1, that will put us at 3, -2, 3. And that is 2, 3 in the direction of 2, 3, -4. So here we are at the point 1, -5, 7. We're drawing this line. This direction here is going to be my 2, 3, -4. And that will land us at the point 3, -2, 3. All we had to do was choose a parameter that was convenient for us. So I said the given point 1, -5, 7, that's going to happen when t is equal to 0. And 3, -2, 3 will happen when t is equal to 1. Once again, we were able to do this because we were able to choose a parameter that was convenient for us. There was no other instruction that said you had to end up at 3, -2, 3 at a certain point. We get to decide when that happens. Now here we are listing the x, y, and z components separately. We can also put this together in a vector form. We can make a position vector out of this. Say r of t is what we've been using. So we can also list this as a position vector. We can also bring calculus thinking into this. This is supposed to be a line. The derivative of a line should be a linear, the derivative of a linear function should be a constant. And that constant will be the slope. Let's see if that happens. Yesterday, we supposed that we could probably just take the derivative of this position vector by taking the derivative of each of the components. We just guessed at that, and turns out we were right in that guess. Our intuition serves us well. So if I do r prime of t, I get the derivative of 1 plus 2t is 2i. The derivative of -5 plus 3tj is plus 3j. The derivative of 7 minus 4t is minus 4k. This is the direction that we wanted to go with. This is the slope of our line. Derivative of a linear function is constant. And that constant is the slope of the line. Oh, but we're in Calc 3, so direction. Just like we planned. Questions? How's everybody okay? Where I'm more on top of things and people were showing up in larger numbers on a regular basis, this would have been a quiz on parameterized curves. I would not have told you how to find the parameterized version of a line. I would have just said, do it. Write a position vector that describes this line. I would not allow you to look anything up. I would have made you guess, and this is what you would have guessed. The reason I know that is that I've done that before, and this is what people guess. Just variations of start here, go this direction. Any questions? Comment? A lot of times that's one of the things that's going on in a math class that makes it difficult is that we'll have some kind of intuition about what we're supposed to do, but we're not really sure about the mechanics of what we're supposed to do. And so the real understanding is when our intuition and our mechanics match up. Think back to integration by substitution. We know it's just an anti-chain rule. And after the first couple of examples, if we just do like really standard examples, I give you stuff that we've just found by using the chain rule and ask you to integrate it back to the original. It becomes pretty obvious the pieces that are there, why the pieces are there and what needs to be there. But we still have to put the mechanics on top of it so that we can recognize, we can get better at recognizing when it will and will not work. So always remember that a lot of times our intuition is going to outpace our mechanics, and understanding is best when those two are close together. Because when those two things are close together and our intuition and our mechanics match up, we can begin to start explaining things to other people. Once we can start explaining things to other people, that's when we really know what's going on. That should be our goal, be able to explain things to other people. If the people in this room comprise this entire class, that's how every quiz and test would be. You would sit down and explain shit to me. And they're like, oh, tell me about these parameterized curves. And then you would explain it to me. But ain't nobody got time for that, so. Any questions? Comments? Problem 2 is clearly just problem 1 starting with the points rather than the direction. But we're going to do the same thing that we did back in elementary algebra. If I give you 2 points and ask for the equation of a line, the first thing you do is find the slope. You use the 2 points to find the slope. Hopefully, you don't think I'll use the slope formula, because using the slope formula is trash. If you have to use the slope formula, that means you don't understand how slope works. This is especially true if you get a little formula card and you actually write down the slope formula on the card. So like when I'm doing elementary algebra, I say, oh yeah, you bring a note card in. But if your note card has the slope formula written down on it, I just flunk you right there. It's like, oh, you don't understand what's going on. Therefore, you don't get, I'm just kidding. I wouldn't do that. I never ask for the cards because sometimes the students want to write on the card, Leach sucks. And that's fine. So like during the test, they're like, oh, and then they could read that and like, oh yeah, that makes me feel better. So I can tell because like during the test, I just have to look up and students are looking at me and they're all mad. They try to hide it, but I can tell. Totally okay. There are a lot of requirements that I think there should be for things. There should be a lot of different drafts, right? Right now, when we talk about the draft, where you're either thinking about fantasy football or like the military, right? You got to register for selective service. But I think there should be drafts for lots more things. I think by the time that you turn 21, you have to be in the retail draft. You have to work retail for 6 months, interacting with the public. That should be just a requirement. Before you're allowed to go out in public as an adult, you have to work retail for 6 months. You have to do your retail service. And by retail, I mean it could be waiting tables. I know that's not traditionally what we think of retail. Or you could work in like a clothing store. But you have to serve as an apprentice in retail, either waiting tables or retail or maybe even barista for 6 months before you're allowed to go out in public as an adult. If you want the advanced clearance to do things like travel, you have to work the front desk at an airport. And you have to deal with travelers because that's the advanced form. You have to deal with travelers. You know what I mean? You walk into a store and you see angry customers and you can see exactly who has never worked retail. You see behavior in restaurants like, well, that person never waited tables. That person never tended bar. You know what I mean? That would be an upgrade. Tending bar. I know it's ridiculous that you'd have to do that before 21, but remember, you're an apprentice. You're assisting someone. They're training you to do this. So, and I think one of the requirements for being a teacher is that you have to be a game master for a tabletop role-playing game. So, and then your evaluator evaluates, are you being confrontational? Are you playing Dungeon Master versus players or Dungeon Master work with players? Because if it's a versus, if you're being adversarial, they say, I'm sorry, but you are not psychologically qualified to be a teacher. Go work on yourselves and then you come back. Do you know what I mean? Anyway, what are we talking about? So back from in elementary algebra, if I said find the equation of this line and I gave you 2 points, you would start off by finding the slope of the line containing those 2 points. You would use the 2 points to find your direction. So we have 1, -5, 7. And the point 3, -2, 3. And we just think we go from 1 to 3. Well, that's in the x direction, 3 minus 1. -2 minus a -5. And 3 minus 7. These are the delta x, the delta y, and the delta z. How much does x change? From 1 -5, 7 to 3 -2, 3. Here's your delta x. Here's your delta y. Here's your delta z. Now, in this case, I just said I'll start at 1 -5, 7 and end up at 3 -2, 3. -4. Thank you. So our direction vector is 2, 3, -4. Now I said we're starting off at 1 -5, 7 and ending up at 3 -2, 3. We're just building a line. So it might be the case where you say, well, I start at 3 -2, 3 and end up at 1 -5, 7. So that works out just the same. If we just, it would just be pointing in the opposite direction, which is parallel to our original direction. So that's totally okay. So if we did 1 minus 3, that's -2. And if we did -5 minus a -2, that's -3. And 7 minus 3 is +4. So we ended up with -2, -3, 4. That's still parallel to our original. This would just be the y direction. And we're still describing the same line. Now, when we parameterize it, it's pointed in the other direction. If we parameterize this, it'd be pointed in the other direction. But we're still describing the same line. And once again, we can just change the direction by reversing the parameter. Change the t with a -t, and everything goes the other way. Any questions? Today, Calc 3 is not a rehash of just Calc 1 and Calc 2. Today, Calc 3 is a rehash of elementary algebra. Man, we went way back. Notice that what we did is the same stuff that we did back in elementary algebra. Find the equation of a line, or find the equations of a line. Note that we're describing the same line, even if we use the y direction, going in the opposite way. 1 minus 2t plus -5 minus 3t plus 7 plus 4t just describes the same line. It's the same collection of points. We're just laying them out in the other direction. We can also start at 3, -2, 3. So we really shouldn't say find the equations, the parameterization. We should just say find a parameterization. So good news. We have an uncountable infinity of choices in how to parameterize this line. Bad news. We have an uncountable infinity of ways to parameterize this line. And that means we have to pick one. So what we're going to do is build a circular spiral starting at 3, 0, 0. So that's down on the XY plane. And it's going to go around once, like building a big spiral staircase. It goes to a point 10 units above where we start by making a big circle. So the top view on the XY plane, we're not going to see the vertical translation. We're not going to see how we're going up the stairs. So from our XY plane, we're just going to see a circle. Starting off at 3, 0, 0. And since this is a top view, I can't see the 3D coming out the page. But it starts off at 3, 0, 0 and goes around once and ends at 3, 0, 10. Up here at the top. So it starts here, it goes around and ends up 10 units above where it started. Hard to line up. Nope, missed. Hard to line up my eyeball with. So the pen shows up on the camera here. Now remember, we have a lot of control over where things are. So it probably makes sense to have the 3, 0, 0 be at t equals 0. We can choose our parameterization to start whenever we want. 0 seems to make sense. So let's say this at t equals 0. We'll sort this part out later. Let's see what else we got. This is our top view. So this is looking at this spiral from the XY plane. Let's look at the spiral from the side. Let's look at the XZ plane. So if we look at this spiral from the side, we're going to start off at 3, 0, 0, and we're going to go up to 3, 0, 10, which will be directly above this point, 10 units up. This is the vertical translation that we can't see from our top view. There's some stuff that we're going to have to fill in. So if we imagine our staircase going around and then ending up up here, then this is, we can get the coordinates of this point on the other side. That's going to be at -3, 0, that we can read just from the XY plane. This should be halfway up because we're halfway around the circle. We should be halfway up at the top. So we're going to say this is 3, 0, 5. -3, 0, 5. So from the side view, I'll have -3, 0 in the Y that we can't see because that's forward and back, and then halfway up at 5. we're making a circle starting off at 3, 0, going all the way around to 3, 0. So we're probably going to be just recycling our circle from before, where x is cosine of t. And this is certainly suggestive of that. Because x, if I put x and z together, I'm just going to end up with this cosine graph. So when it starts off, if the positive y is coming straight out at us, this x starts coming out at us, then it goes back down into the paper, then this second half where is behind the paper. So if we set this up where the positive y-axis is coming out of the page, then the y values are going to be positive until it gets back to negative 305. So it goes up and around. Now it's behind the page, and then comes back to the page. You still have to sort out when these t's are happening. Our second side view will be y and the yz plane. Now in our second side view, let's have the x-axis coming out of the page. So the x-axis is sticking out of the page like this. I'll point it at the camera. So when I plot the point 3, 0, 0, I'm not going to be able to see the 3 part. So that's just going to be out the page, out here in front. So 3, 0, 0 will happen here because we can't see the x. Here's 3, 0, 0 at t equals 0. Then it goes around and ends up here at 3, 0, 10. Once again, we can't see the 3 parts. So I'm just plotting the point 3, 0, 10. That's the part of the point that we can see, the 0, 10. This point in the middle, negative 3, 0, 5, I can't see the negative 3 part. I can only see the 0, 5 part. So that's going to show up here. So notice that these 3 points are because I can't see what's going on with the X. I can only see what's going on with the Y and the Z from this particular side view. I don't see that stuff coming out in front or moving behind. So at this point, I'm going to want to notice these top and bottom points. Down here at the bottom, X is 0, Y is at -3, and Z is, well, we'll have to figure that out. And up here, that's right. That's why I wanted to use 12. I wrote 10 originally. I'm like, oh, no, you should use 12. I'm like, oh, I already wrote 10. I'm going with 10. And then back, all right. I forgot I had to divide by 4. Oh, well. 7.5 is a thing. Now, up here at the top, the X is 0. Y is going to be at +3 because we're making a circle. And then we'll have to sort out where the Z value is. These points are going to be halfway between 300 and -305. So I'm just dividing into 4 parts. So I don't see the, so since this goes from 0 and then 5, and this one is halfway, this one's going to have to be at 2.5. And then this one's going to have to be at 7.5. Now remember, I can't see what's going on with the X. I can only see what's going on with the Y. So I'm going to plot the point 3 and 2.5 on my second side view. So 3 and 2.5, 3 and 2.5. So there's that point. And then halfway, and then on the other side will be 0, -3, 7.5. Y is -3, and Z is 7.5. This makes sense because I made a circular spiral, so I'm clearly just referencing our previous parameterized circles. And in our previous parameterized circles, Y was sine of t because tradition. So it makes sense that from the YZ perspective, I end up with this sine graph. Any questions? So these points, 0, 3, 2.5, and 0, -3, 2.5, on our side, our first side view with X and Z, I can't see the Y. So I can see the point 0, 3. And I can see the point 0, -3, 7.5. Sorry, not 0, 3, 0, 2.5, and 0, 7.5. Question? Note that what I didn't try to do is draw a 3/4 view of this spiral going up. The main reason for that is that I can't. I'll just be upfront about it. It never comes out well. You're going to have to go look up a picture of a spiral or use the theater of the mind And imagine a spiral going around once up 10 feet. Any questions? Comments? Stat on one. Or for engineers, build one. And then 3D print it. I don't know if you can 3D print this. Becomes much more complicated when it's 4-dimensional anyway. So I know that's a cop out, but like I said, I cannot draw one in 3/4 view. How's everybody okay? Note that we didn't figure out what the values of t were, and we didn't sort out what the parameterization should be. But there's going to be some cosine for the x, some kind of sine for the y, and then we're going to have to figure out what's going on with z. All right, that's it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.